The following scenario is hypothetical and presented for educational and entertainment purposes. 10 seconds is all it takes to erase the sky. In our familiar history, a fragile tube of glass and metal quietly transformed the human mind. The telescope turned distant lights into worlds, speculation into measurement, curiosity into the engine of modern science. But imagine a timeline where that fragile tube never appears. No curious artisan grinds the first precision lenses. No scholar raises a device toward the moon and realizes the heavens are not perfect. The sky remains what it had always been to ancient civilizations, a distant ceiling of light, beautiful but unreachable. The consequences begin subtly. Without telescopes, astronomy freezes at the level of naked eye observation. Humans can track planetary motion with mathematics, but they cannot verify what those wandering lights truly are. The Copernican model survives as a mathematical convenience, but the decisive evidence that once shattered the old geocentric worldview never arrives. No one observes the phases of Venus. No one sees Jupiter's moons orbiting something other than Earth. The universe remains philosophically uncertain. Scientific revolutions, contrary to popular myth, rarely occur because of a single idea. They happen when observation crushes doubt. In this alternate world, doubt survives. Universities debate cosmic models for centuries without resolution. The heavens cannot be tested, only argued. Without observational astronomy pushing optics forward, the science of precision lenses develops slowly. Microscopes appeared decades later than in our world, and even then they remain crude. Biology therefore stalls. The invisible microbial universe stays hidden far longer than it should, and hidden microbes quietly reshape civilization. Medicine continues to operate under ancient assumptions about imbalance and miasma. Epidemics rage through cities with little understanding of their true causes. Public health reforms emerge slowly because no one can prove the existence of microscopic pathogens. Mortality remains high well into what should have been the modern age. But the telescope's absence creates another, less obvious fracture. Navigation. In the real timeline, telescopic astronomy refined star catalogs and celestial navigation with incredible precision. Sailors learned to measure longitude more accurately. Global trade accelerated. Empires rose on the back of reliable navigation across dangerous oceans. Without telescopic astronomy, navigation improves only incrementally. Maps contain larger uncertainties. Oceanic voyages remain riskier and slower. Exploration continues, but global integration crawls instead of sprints. The world economy grows unevenly. Certain coastal powers invest heavily in mechanical timekeeping and experimental optics to compensate for the missing precision in celestial observation. Others cannot afford such research. Technological inequality begins quietly here, not with computers or rockets, but with the simple ability to measure the sky more accurately than your rivals. This inequality compounds over generations. Scientific cultures that might have emerged across the globe instead cluster in a handful of wealthy regions capable of funding long-term observational experiments. Meanwhile, vast populations remain trapped within technological stagnation, simply because the sky refuses to reveal its deeper structure. The irony is devastating. Humanity still sees the stars every night. They just cannot truly study them. And somewhere in the late 18th century of this alternate world, a mathematician studying planetary motion begins to suspect something disturbing. The equations suggest the universe is far larger and stranger than anyone can prove. But without a telescope, there is no way to check. The mathematician's suspicion spreads slowly, like a ripple moving through still water. His equations predict irregularities in planetary motion that no naked eye can confirm. The mathematics insists that distant bodies must exist beyond the visible planets, exerting subtle gravitational influence. Yet the sky refuses to cooperate. Every night it presents the same unyielding ceiling of light, as smooth and mysterious as it had appeared to ancient civilizations thousands of years earlier. In a world without telescopes, mathematics becomes both the sharpest and the most dangerous scientific tool. By the early 19th century, in this alternate timeline, scholars begin constructing elaborate celestial models entirely through calculation. Complex gravitational systems are proposed to explain minute deviations in planetary paths. Entire invisible planets are hypothesized. Some even suggest massive rings of unseen debris orbiting the sun. But none of these ideas can be verified. Science begins to split into two rival cultures. One side believes mathematics alone can reveal reality. The other insists that without observation, equations are only elegant guesses. The tension between these camps quietly slows progress across multiple disciplines. Funding bodies, monarchs, and early industrial governments become cautious. Why invest vast resources in theories that cannot be directly tested? The absence of telescopes does not simply delay astronomy. It poisons the feedback loop between theory and observation that normally drives scientific revolutions. Physics suffers the consequences next. In the real world, telescopic observations of planetary motion and stellar parallax helped refine measurements of gravity and distance on cosmic scales. Those measurements fed directly into breakthroughs in classical mechanics and later into the foundations of astrophysics. In this alternate timeline, those precise measurements never arrive. The scale of the universe remains ambiguous. Is the solar system enormous or merely large? Are stars distant suns or small lights embedded in a celestial sphere? Philosophers argue endlessly. Without stellar parallax measurements, the true distance to stars cannot be proven. Entire cosmologies remain plausible centuries longer than they should, and this uncertainty spreads beyond astronomy. Industrialization still occurs, but its pace changes. Scientific instrumentation evolves slower because optical engineering lacks the intense pressure created by astronomical research. High-quality glassmaking becomes a niche craft rather than a massive industry. Precision grinding of lenses develops inconsistently across nations. This matters more than anyone realizes at first. Optical technology does not only build telescopes, it enables microscopes, spectroscopes, cameras, and eventually entire branches of physics and chemistry. Without early investment in high-precision optics, the technological tree grows crooked. Photography emerges decades later. Spectroscopy, one of the most powerful tools in scientific history, barely exists. Scientists cannot analyze the chemical composition of stars because they cannot properly capture starlight. The stars remain silent. By the mid-19th century, wealthy scientific societies attempt to solve the problem with massive naked-eye observatories. Giant mechanical instruments are constructed to track planetary motion with extreme precision. Towers rise across Europe and parts of Asia, where astronomers spend entire careers measuring angles between faint points of light. But the ceiling of the sky does not open. Meanwhile, another quiet transformation unfolds on Earth. Global trade networks remain fragmented compared to the rapid expansion seen in our timeline. Navigation errors accumulate across long oceanic routes. Shipping losses remain common. Insurance markets inflate dramatically to compensate for navigational uncertainty. Only the richest maritime powers can afford the expensive chronometers and mechanical devices needed to reduce those risks. Poorer nations fall behind. The economic gap widens slowly, almost invisibly at first, like tectonic plates drifting apart beneath the ocean. Regions with strong engineering traditions attempt experimental optical research, but progress remains scattered and slow without the catalytic breakthrough that telescopes once provided. Generations pass. Humanity enters what should be the modern scientific age, yet the cosmos remains fundamentally mysterious. Universities still teach competing models of the solar system. Some textbooks cautiously suggest the existence of unseen planets, but none can be shown. And then, sometime in the late 19th century, a new anomaly appears. Astronomers tracking Mercury notice that its orbit shifts slightly over time in a way that no known mathematics can explain. In our world, telescopes would have revealed the details necessary to study the phenomenon. In this world, the sky continues to hide its answers. The anomaly in Mercury's orbit becomes the first true crisis of modern science in this alternate world. For decades, astronomers armed only with mechanical instruments and naked-eye observation had prided themselves on the precision of their measurements. They could calculate planetary positions centuries in advance. Maritime nations relied on those predictions to chart safer routes across unpredictable oceans. Governments trusted the stability of celestial mechanics as proof that the universe followed elegant, reliable laws. Mercury quietly shatters that confidence. Each time the planet completes an orbit around the Sun, its closest point shifts slightly forward. The motion is tiny, barely noticeable across a single generation, but meticulous records accumulated over decades reveal the pattern unmistakably. The equations that describe gravity can almost account for it, but not entirely. Scientists respond the only way they can, with more mathematics. A hidden planet inside Mercury's orbit is proposed. Some call it Vulcan. Theoretical charts map where it should appear during rare alignments near the Sun. Observatories across several continents coordinate efforts to search for the phantom world during solar transits. But they have no telescopes. Attempting to detect a faint body near the Sun using only the naked eye becomes a desperate exercise in patience and luck. Astronomers stand in scorching daylight, shielding their vision with experimental filters made from smoked glass and layered minerals. Occasionally, someone claims a brief sighting of a dark dot crossing the solar disk. Each claim spreads through academic circles with cautious excitement, and each claim collapses under scrutiny. The phantom planet refuses to appear consistently. The anomaly in Mercury's orbit remains unsolved. This single failure begins to fracture scientific authority. For centuries, scholars had insisted that the universe was fully understandable through reason and careful observation. Now, one of the most basic predictions of celestial mechanics refuses to cooperate. If gravity cannot fully explain the motion of a nearby planet, what else might be misunderstood? Public fascination grows. Newspapers publish diagrams of invisible planets and speculative maps of the inner solar system. Some writers suggest entire swarms of hidden bodies circling close to the Sun. Others propose that gravity itself may behave differently near intense heat or light. But without telescopic precision, every theory floats in uncertainty. Meanwhile, the industrial world continues evolving unevenly. The nations wealthy enough to sustain large observatories also dominate engineering and manufacturing. Their universities produce generations of mathematicians attempting to refine celestial models that can never quite be verified. Poorer regions face a harsher reality. Without strong scientific infrastructure, they depend on imported technology that itself advances more slowly than it should. Medical research remains limited. Without powerful microscopes, the microbial basis of disease is still debated even in the early 20th century of this timeline. Epidemics continue to strike cities with devastating regularity. Life expectancy rises, but painfully slowly. The absence of telescopes has created a strange bottleneck in human knowledge. Astronomy cannot advance, optics stagnate, microbiology struggles, and several branches of physics develop without the observational pressure that once forced rapid breakthroughs. Even electricity progresses differently. Spectroscopy, normally critical for understanding atomic structure, remains underdeveloped. Physicists build theoretical frameworks for matter, but experimental confirmation lags far behind. Laboratories rely on crude optical devices that distort or lose critical wavelengths of light. The universe remains largely unreadable. By the early 20th century, humanity has built railways across continents and harnessed electrical power, yet the stars are still mysterious points. No one has seen the mountains of the moon clearly. No one has observed the rings of Saturn. No one has witnessed the swirling storms of Jupiter. To most people, those wonders simply do not exist. Children grow up imagining the planets as smooth, glowing marbles moving silently through space. And yet the mathematical anomalies keep accumulating. Mercury's orbit remains unresolved. Slight irregularities appear in other planetary calculations as well. Theoretical physicists begin exploring radical alternatives to classical gravity. Some suggest that space itself might possess hidden curvature or invisible structure influencing motion. But again, observation cannot catch up. The sky is still locked. Then, a young physicist studying gravitational mathematics proposes something deeply unsettling. According to his calculations, gravity might not be a simple force at all. It could be the result of space bending around massive objects. In our familiar timeline, telescopes would soon provide critical evidence supporting such a theory through astronomical observation. In this world, the theory arrives decades before the tools capable of testing it. By the time the young physicist publishes his radical theory about gravity, the scientific world has already grown accustomed to living with unanswered cosmic questions. His equations describe space not as an empty stage where objects move, but as a flexible structure that bends under the weight of matter. Planets follow curved paths not because an invisible force pulls them, but because space itself guides their motion. Mathematically, the theory is breathtaking. It explains Mercury's strange orbital shift with perfect elegance. The numbers align. The anomaly disappears inside the curvature of space-time. For the first time in nearly a century, the mystery appears solvable. But the solution arrives with a cruel limitation. The theory demands observational proof that cannot exist in this timeline. In our familiar history, telescopes allowed astronomers to measure how starlight bends when it passes near the sun during a solar eclipse. That tiny deflection became one of the most famous confirmations of modern physics. It turned a daring theory into accepted reality. Here, the sky refuses again. Without telescopes capable of tracking faint stars close to the sun, the bending of light cannot be measured with sufficient precision. Astronomers attempt eclipse expeditions using crude optical instruments, but the results are inconsistent. The distortion of light is simply too small to detect reliably. The physicist's theory remains suspended in scientific limbo. Some universities teach it enthusiastically. Others dismiss it as mathematical speculation. For the public, the debate feels increasingly abstract, disconnected from daily life. After all, most people still live in a world where the moon is a bright disk with no visible detail, and the planets are wandering dots. The deeper tragedy unfolds quietly across the 20th century. Because the telescope never accelerated optical science, entire technological ecosystems develop slower than they should. High-resolution lenses, precision mirrors, and advanced glass manufacturing never become dominant industries. Laboratories rely on improvised optical equipment that struggles to capture faint or distant signals. Astronomy remains a largely theoretical discipline. But astronomy in our world did more than study distant stars. It drove the invention of detectors, imaging systems, and signal amplification technologies that later shaped telecommunications, satellite systems, and digital imaging. Without that push, the technological ladder shortens. Early rocketry still appears, largely motivated by military ambition rather than scientific exploration. Engineers imagine reaching space, but their understanding of celestial bodies remains strangely primitive. The moon's surface is still a mystery. No detailed maps exist. Landing on it becomes an almost reckless gamble. As a result, space exploration progresses cautiously. Governments hesitate to fund missions into an environment they barely understand. Sending humans beyond Earth feels less like exploration and more like blind navigation into darkness. Robotic probes are proposed, but designing reliable guidance systems proves difficult without precise astronomical reference points. The space age begins decades late, and when it finally starts, it starts unevenly. A handful of wealthy nations, already far ahead in engineering and industrial capacity, invest heavily in experimental optics during the mid-20th century. They recognize that the bottleneck lies not in mathematics, but in the ability to see. Massive research programs attempt to reinvent optical science almost from scratch. Slowly, painfully, the first true telescopes begin to emerge, centuries after they should have appeared. But the delay has already reshaped the planet. Global inequality has hardened into something structural. The nations capable of funding advanced research dominate every emerging technological field. Regions that once might have developed their own scientific institutions now struggle to catch up with a knowledge gap that spans generations. In this world, billions of people grow up in societies where modern medicine arrives late, where technological infrastructure develops slowly, and where education systems lack the scientific revolutions that once inspired curiosity about the universe. All because one small invention never happened when it should have. When the first modern telescope of this delayed era finally turns toward the moon, the scientists operating it are stunned into silence. Mountains rise from the lunar surface, vast craters scar its landscape. The smooth, glowing disk that humanity believed in for thousands of years suddenly becomes a violent geological world. For the first time in this timeline, the sky finally opens. But by then, centuries of lost progress have already rewritten the destiny of civilization. And the most unsettling realization arrives only after that first observation spreads across the scientific world. If one missing scientific step could delay humanity's understanding of the universe for hundreds of years, how many other breakthroughs might still be waiting in the dark simply because no one has built the right tool yet?